Hello, welcome to the sixth video in Light as a Particle. In this one we're going to look at the Compton momentum equation, sometimes also referred to as the Compton effect or Compton scattering. So who, first of all, is this Compton person? Well, he was around in 1892 to 1962, Arthur Holly Compton. And that's what he looked like. Writing some of the equations, you may recognize this diagram in a sec. And he did experiments, and what his experiment was, he had a block of graphite and he fired X-rays into the block of graphite, and he looked at what was coming out, and what he would see would be some X-rays would go straight through and nothing would change. But then he would also see other electrons which were scattered, and some of these electrons would either have the same velocity that they went in with, but others would have a new velocity. He would also see electrons that were knocked out of the target, and that was the observation, and he needed to make an explanation for it. So he showed that X-ray photons behave like particles with momentum. Effectively, it's collisions with a transfer of momentum. Now that's a major thing, because photons weren't thought of as being particles. Momentum is very much a particle property, whereas photons were thought of at the time, or previously, as effectively waves. But now they were behaving like particles. And he received the Nobel Prize in Physics in 1927 for that. And this was just another diagram of his apparatus. He had an X-ray tube that made his X-rays. He had a narrow gap, rather than calling it a kilometer. He fired the X-rays at the graphite, and then he measured what was the result. Now, from this he got this. So he would have an incident photon. This is our X-ray hitting the target, and it would have amount of energy corresponding to HF. It would engage an electron and knock the electron in its direction, so the electron was effectively given a momentum, and a new photon, which is not the same as this photon, was given off, and this would have the energy of HF with a dash, and the frequency of the scattered electron is always less than the incident photon. Did I say electron? Photon. Okay, so that should remember that diagram. And so this is another one in color. So we have the photon, the X-ray photon, electron are effectively at rest. Collision, you get a scattered photon. Now the energy of this is less than the energy of this, and the electron is given off in a certain direction. And so he could measure these angles accurately. And so in terms of momentum, he said that the momentum of the photon plus, so the initial momentum is the momentum of the photon plus the electron, which is 0. Then you have your scattered photons momentum and the momentum of the electron, and you put them together and they make themselves a complete triangle with no gaps, and therefore momentum is conserved. And he worked out that the momentum of a photon, P, is HF divided by C, which is equal to H on lambda, recognizing that F divided by C comes from C equals F lambda, our universal wave equation, where C is the speed of light, of course. So the momentum of the photon, the fact that X-rays have momentum was clear evidence that electromagnetic photons behave like a single particle. So each photon behaves as a particle. Now you should be able to do those questions in your workbook. And in the next video we'll look at Cherenkov radiation. Bye.